What's up, people? Hello, Sasriyakal. What's up? How are you guys doing? A very warm welcome. Sorry for a little delay. Some tech issues, like as always. What is up, people? All good? Hello, what's up? Hi, Michelle, what's up? Hi, Monica. Hum aayega? Hum aayega ya? Hum aa gaya? Bad Hindi, people, bad Hindi. Sorry for that. What's up? I'm good. How are you guys doing? How was your day so far? Hi, Aditya. What's up? I'm awesome. Super awesome. How are you guys doing? Good evening, Gauri. What's up? Hi, Kamal. Welcome, people. I hope all of you guys are doing good. Having a fabulous, fantastic, super califragilistic, day. A very warm welcome to today's session. My name is Anup, and this is your very own Vedantu's 9th and 10th English channel. Before we get started, hit the like button, subscribe to the channel, because why not? It's free. Free? Yes. Yeah. I should, give myself a thumbs up for that. Good job, Anup. Good job. All right. So with that said, people, let's get into today's session without wasting much of your valuable time. By the way, before we get started, how are you guys doing? How's the Josh? Exactly. How's the Josh? All good? Yes. Excited to learn something new today. Because today is the day that we learn about ray diagrams. One of the most important topics in this chapter, ray diagrams, we're going to be understanding today. We'll understand about the standard incident rays and all of the ray diagrams of your concave mirrors. Shall we get started? Kadak. Hi, Jatini, what's up? Thank you, Chaudhary. Me also big fan of you guys. Hi, Shaurya, what's up? Hello, class 9, Shaurya ji. What are you doing here? Chilling out with your seniors. That's good. Netflix and chill in the same way. YouTube and chill now. All right, so people, let's begin today's session without wasting much time. Before we get started, I had asked a small little homework question in the previous one. First of all, a big round of applause for all those beautiful, fantastic people who gave the right answer. Right? So the question was this: a dentist uses a small dental mirror to help magnify the teeth that is there in your mouth. What type of mirror is used in this scenario? Do you know the answer for this, people? Quickly in the chat box. What is it? Yeah, we have quizzes also. We have quizzes in today's session. So quickly join the session on the platform so that you can take part in the quizzes today. Anyone knows the answer for this one? The answer to this question is concave mirrors. They basically use concave mirrors to see what's happening inside your teeth. And these are the homework rockers. We have Hanumant Kokani. Congratulations, Hanuman ji. Then we have Michelle. As always, thanks a lot, Michelle ji. Chota Beam also. My God, Chota Beam. What are you doing here? Then we have Niveda Katayanami. Congratulations again. Fabulous job, people. Fabulous job. Super duper amazing. If you guys want your name to be here next time, answer the homework question. All right, that is asked at the end. Now, people, all those who are watching the session on YouTube, here's what I want you guys to do. All right, I have a lot of quizzes today for you people, but in order to attend those quizzes, you must actually enter into the website. So what you have to do is this: you're watching the session on YouTube right now. Thanks a lot, Deepika ji. All you have to do is go to the description of this video. You'll find a link right here. Watch this session on Wave. So all you have to do is click on this link and it'll directly take you to this page. This is where all you have to do is give access and you're in. Voila. Now, once you guys are in, people, you can actually take part in the quizzes, enjoy this whole session on the platform where you have a lot more features, fun-packed, and you get to enjoy the session to the fullest. All right. So please join the quiz, join through the link into the session, so you can actually take part in the quizzes and answer the quizzes and see yourself on the leaderboards, fastest fingers list, and whatnot. All right. So shall we start? Sir, why was previous session not live? Unfortunately, I couldn't come live. That is why. Sandeep Maheshwari, Noda. I know Maheshwari classes from Kota Factory though. All right. So let's get started, people. Okay. Now, as I told you people before, that what we're going to learn today is basically about the standard incident rays and ray diagram. Now, before I start with this topic, let me tell you why this topic is so very important. The reason why this topic is so very important is, guys, it's because you have ray diagrams in your board exams. It is a short question. 100%, mark my words. You can, I can give you a notary paper with my sign on it. Absolutely, you are going to have questions based on ray diagrams. So it is vital, not important, it is vital that you understand this. But in order to truly understand ray diagrams, you must first understand the sign convention. So what is the sign convention? What are these standard incident rays? So here's what you need to understand, people. When you have a mirror, be it a concave or a convex mirror, it doesn't matter. What we do is we basically draw a line passing through the center of curvature and pole, which is known as what, my people? I'll turn on the chat. What is that line, that imaginary line passing through the pole and the center of curvature known as? In the chat box over here and on YouTube, please put down what is that line called as? If you have a mirror, let's say, exactly, Michelle. Exactly, Navya. Exactly, Ale. Exactly, Aditya. That line is called as the principal axis. Now, you must remember this. Let me tell you why this is so important. Because, people, all the distance that we measure when we talk about ray diagrams is all measured with respect to the principal axis. It is all measured with respect to the principal axis. Now, if that is the case, what is the sign convention? I want all of you guys to go back to your 7th, 8th standard geometry. So in geometry, you would have learned about something called as the Cartesian planes. I don't know if you remember this. There is something called as Cartesian planes where you have something called as the x-axis, x-dash axis, y-axis, y-dash axis. Yes, people, do you remember that? You had learned it in your 7th, 8th standard mathematics. You have probably learned it. I mean, you have learned it, but you remember it? That is the question. You guys remember this? You've actually studied this in your lower grades. Cartesian planes, x-axis, y-axis, x-dash, y-dash. Huh? No? Yeah, no? Exactly. O is the origin. Arre, Chaitanya ji. Awesome. Now, here is the thing, people. I want all of you guys to go back to it. The reason why I want you guys to go back to it is because we are going to be using the exact same logic of Cartesian planes over here also. Let me tell you how. See, guys, in Cartesian plane, if you remember, x-axis was considered to be positive. So you had +1, +2, +3, so on and so forth. X-dash axis was considered as a negative axis. So basically you have -1, -2, -3, and so on and so forth. Y-axis was considered as positive. So it is basically a vertical line. So this is +1, +2, +3, so on and so forth. And then y dash was considered as negative. So that is basically -1, -2, -3, -4, and so on and so forth. Yes, people, you guys remember this, no? This is what you've done in your lower grades. Absolutely. No doubts about it, right? Now, here is the thing, guys. Let me tell you how we're going to use this over here. See, guys, the pole here is the origin. Imagine that the pole is nothing but the origin. Wherever the mirror is kept, that is your y-axis, y and y dash. Which means that if the mirror is kept such a way that it is facing towards your left, all right? I'll just repeat it one more time. I'm going to enlarge my screen just for the sake of it. So just focus here, guys. This is the mirror, all right? You can clearly see that this is the reflecting surface. If the mirror is kept such a way that it is facing towards your left hand side, all right, all distances in front of the mirror where the reflection is happening, that is considered to be negative. All right, just like the Cartesian planes here. Look at the Cartesian planes. Cartesian planes also towards the left hand side is considered to be negative. Here also same thing. Reflecting side towards the left hand side, facing towards the left, that is considered as negative. So what will be the sign behind the mirror, people? The side where there's no reflection happening. What is that side then? Positive or negative? Think. Exactly. This side would be considered as positive. Simple as that. What about the distance above the principal axis? If this is the principal axis, this is the origin, what about the distance above the principal axis then? Above the mirror? Exactly. Positive. Below the mirror is considered to be negative. As simple as that. That's all. So if you know your Cartesian planes, if you remember your Cartesian planes, your ray diagram, when you're drawing your ray diagrams, your sign convention also becomes very, very, very simple. Now, why is this Cartesian plane so important? Why is this sign convention so important? Because you need this for your numericals. Without this, you cannot do your numericals. I mean it, people. Without this, you cannot do your numericals. This is very, very, very important for your numericals. Getting it? Without this, you cannot do your numericals because absolutely you will get it wrong. Absolutely you'll get it wrong without remembering this. So please remember, guys, one very important thing you need to remember is no matter what sort of mirror it is, this is a concave mirror, be it a convex mirror also, it really doesn't matter. I have a convex mirror here with me. I'll just take that also out. So this is a convex mirror, this is a concave mirror. We will always keep the mirror facing the left hand side, facing towards the left. The reflecting surface that you have will be facing towards the left itself all of the time. Got it? It doesn't matter whether it's a concave mirror or a convex mirror. The reflecting surface that you have will be facing towards the left. The reason why we do this is to keep everything normalized. Now, it is not that I can't turn the mirror. It is not that I can't turn this mirror right towards the right. The only reason why we keep it this way is to standardize everything. That's all. So when you keep the mirror facing towards the left hand side, all distance facing the mirror, that is towards the mirror, to in front of the mirror is considered as negative, behind the mirror is considered as positive. It is just to standardize it. There's nothing wrong in turning the mirror on, but we don't do it just because we want to standardize everything. Is that clear, people? So always keep it like that. Got it? Be more louder. I don't think I can go any louder than this, but I hope you guys can hear me clearly. Guys, is my voice not loud enough for you people? Let me just check it on the YouTube platform as well. Just give me 1 second, people. Let me see if my voice is heard or not. 1 second. Just give me 1 second. I'll just check if my voice is heard or not. It's clear, huh? Wait. Sorry. It's clear. Voice is clear, no? Addi. Loud enough. No. I'm shouting from that time. What is this, people? Okay, now. With that out of the picture, let's talk about your ray diagrams. See, guys, like I told you before, we always keep the object in front of the mirror. We always keep the object in front of the mirror facing towards the left hand side. So we always keep the object on the left hand side facing the mirror. So this side in front of the mirror is taken as negative. The side behind the mirror is taken as positive. Above the mirror is taken as positive, and below the mirror is taken as negative. This is all you need to understand. So here is the thing, guys. Let's say there is an object kept in front of a concave mirror. Let's say there's an object kept in front of a concave mirror. Or let's say it's kept in front of a convex mirror. Now the thing is, people, the special thing about these concave convex mirror is that depending on where you keep the object, the kind of image that is formed might also differ. Now, what do I mean by this? I want all of you guys to focus on this concave mirror right now. All right, I want all of you guys to focus on this concave mirror right now. All right, I'll just make this picture a little bigger so that you can clearly see it. I want all of you guys to focus on this right now. Now, how does the mirror look like? How does the mirror look like? I mean, what does the image look like? All of you guys put it on the chat box. What does the image look like? You can clearly see the camera over here. So what does the image look like? Like, how does the camera's image? Very clear though. Enlarge, it's a little bigger. It's actually a little bigger. Now, if I take it backwards, as I move backwards, can you see that the image that you get is actually getting a little bit more hazy? Can you see that? It's getting hazier and hazier. Understanding? The kind of image that you get. Now, if you notice carefully, the image right now is upside down. Can you notice this? It is actually upside down now. It is no more upright. Can you see this? It is upside down. As I bring it closer again now, it is becoming upright. But as I take it further and further away, it is becoming upside down now. It is getting inverted. Why? Why is that? That is what we are learning today. Because with this ray diagram, you can actually find out where and when will you get an inverted image, where and when will you get an enlarged image. That is why this ray diagram is so very important. Because with the help of ray diagrams, you can actually predict what type of image you're going to get. What is the kind of image you're going to get? Okay, let's take a convex mirror now. All right, we'll do the exact same experiment with this one now. All right, look at this one now. All right, everyone look at this one. Image, yes. As I take it further away, there is not much change happening except for the fact that the image is getting smaller and smaller. Yes, it's getting more smaller as I take it further and further away. It's getting more smaller and smaller, right? Here is the thing, guys. The type of image that is formed in both concave and convex mirror depends on where the object is kept. So using the ray diagram, you can actually tell or predict what type of image is formed, what are the properties of the image, and where should you keep the object if you want a certain type of image to be formed in that position. Getting it? That is why ray diagram is important. Understanding, people? That is the importance of this. It helps you to predict, it helps you to figure out where and what type of image is formed in what position. So what we're going to do is very simple. We're going to take an object, and what we'll do is we'll bring this object or change the position of this object every single time. So let's start with one thing. Let's say there is an object that is placed in front of a concave mirror, and the object is placed at infinity. Infinity in the sense very, very far away. Now that infinity can be, it can be the sun, it can be a tree which is about 5 kilometers away, it can be 1 kilometer away. It really doesn't matter. There is an object that is kept very, very far away. Understanding the scenario, people, I have an object which is kept very far away. Now the sun is about 150 million kilometers. All right. Now I want all of you guys to understand this. See, people, this mirror has a focal length of 20 centimeters. Now you guys remember what focal length is. I've already taught you this in the previous session. The focal length of this particular mirror is 20 centimeter. So let's say there is a tree at 5 kilometers away. All right, about 5 kilometers away. Now for this mirror, that 5 kilometers can also be infinity. Understanding? 1 kilometer also can be infinity. Because if you look at in terms of centimeters also, it's very, very far away. It's very, very far away, right? So that is what you need to understand. Infinity can be 100 meters, it can be 1 kilometer, it can be 10 kilometers, it can be 150 million kilometers also. Understanding? There's no quantifying it. It depends on where the object is kept. So if you have an object which is kept very, very far away, then we say that the object is at infinity. Now people, remember, when we are doing this, we will be using 3 standard incident rays. All right. When you talk about ray diagrams, we're going to be using 3 standard incident rays. I'll just draw that first before I come to this. 3 standard incident rays. Again, you guys can do it with me if you want to. So what I'm going to do is I'll just draw 3 concave mirrors. All right. I'll just draw 3 concave mirrors over here, 3 circles. One sec. I'll just draw it so that you guys can easily understand what I'm talking about here. All right. So let me just erase this one out. 1 second, people. Let's just try to figure this out. All right. Done and done. All right. Now here's the thing, guys. Exact same thing. All right. We'll do the parallel, the principal axis. On all the 3, we'll do some principal axis as well. Okay. Now there are 3 standard incident rays. All right. There are 3 standard. Imagine there's an object kept in front of the in front of a concave mirror. The first standard incident ray is if there is a ray of light which is parallel to the principal axis, after reflection. Let's say this is the focus, let's say this is the center of curvature, this is the pole. All right, exact same thing over here also. This is the focus, this is the center of curvature, and this here is the pole. Pole, focus, and center of curvature. If there is a ray of light parallel to the principal axis, then after reflection, this ray of light will always pass through the focus. Got it, people? If you have a ray of light parallel to the principal axis, after reflection, this ray of light will always pass through the focus. This is the first standard incident ray. Let's say there is a ray of light which is passing through the focus. What will happen to that then? If you have a ray of light passing through the focus, let's say the object is kept somewhere over here. Let's say that the object is kept somewhere over here. Why am I not able to write? Okay, I am not able to write for some reason, guys. That's weird. All right, let's say there's a ray of light passing through the focus. Okay, I'm not able to write for some reason. Can you guys see? Okay. What is the reason for that? That is some weird thing. Now, one second. Let me just reload the site. Just give me 1 second, people. That happens. What happens? All right, just give me 1 second. I'm back, people. I'm back. I don't know what happened to that. Okay, I think it's because of the hotspot. All right, anyways. Okay, let me just, like try to resize this thing now. Wait a second. All right. This is bait. Okay. Okay. Much better. All right. So people, let's focus back. Let's come back to this. Let's say there's a ray of light passing through the focus. All right. There's a ray of light passing through the focus. Then what's going to happen is that after reflection, this ray of light will be parallel to the principal axis. It is just the opposite of the first case. See, in the first case, it was parallel to principal axis. After reflection, it went through the focus. The second one is if a ray of light is passing through the focus, after reflection, it will become parallel to the principal axis. In other words, if this is the first ray diagram and this is the second standard incident ray diagram, this is basically interchangeable. Understanding? It is interchangeable. If one is passing through the focus, after reflection it is becoming parallel. If it is parallel to the principal axis, after reflection it is passing through the focus. It is interchangeable. It's like Uno reverse card. Getting it? Uno reverse. Understanding? It's like that. It's the opposite. The reason why this is so is because of something called as the principle of reversibility. Light always follows the exact same path, and that's exactly what's happening over here also. The last but not the least is this, people. If you have a ray of light that is passing through the center of curvature. Let's say there's a ray of light. Let me try to resize this one as well. Just give me 1 second, people. I'll just keep it over here so that you can clearly see it. If you have a ray of light passing through the center of curvature, let's say there's a ray of light passing through the center of curvature, then what's going to happen to that is, okay, let's just draw the diagram itself. All right, 1 sec, people. Again, I don't know why the tech is acting so weird today is beyond my understanding. Let's see if we can sort that out. All right, a ray of light passing through the center of curvature. If a ray of light is passing exactly through the center of curvature and if it's falling on the mirror, then after reflection, this ray will follow the exact same path. In other words, it will get reflected back in the exact same manner. So what is going to happen is this thing will also follow the exact same path. Now, why does this happen? Because people, if you have a certain point, let's say there's a point. All right, this is the point. If that is the point, and if you want to draw normal to that point, the normal will pass through the center of curvature. All right. If I take any point on the mirror and if I want to draw normal to that point, the normal will be passing through the center of curvature. So if a ray of light is incidenting exactly at the normal, what will be the angle of incidence, people? Put it on in the chat box. What will be the angle of incidence if a ray of light is exactly falling on the normal? Exactly 0 degrees. 0 degrees. So after reflection also, what will be the angle of reflection? 0 degrees again. Because every ray of light follows the laws of reflection. So here, if the ray of light is passing through the center of curvature, angle of incidence is 0. So angle of reflection will also be 0. That means it will retrace the exact same path. Now, why am I telling all this, people? Is because we have 6 ray diagrams for concave mirrors. All right. 2 ray diagrams for convex mirrors. 6 ray diagrams for convex lenses and 2 ray diagrams for concave lenses. Now you tell me, guys, is it easier for you to by heart 16 ray diagrams or to understand it? Would it be easier for you guys to understand the ray diagrams or to by heart it? Understand it, no? That is why. That is why I'm telling you this. Because if you understand this one that I'm just telling you right now, trust me, no matter what sort of ray diagram is asked in your exams, you would be able to do it with 100% confidence. You just need to remember these 3 ray diagrams. That's all. If you remember these 3 standard incident rays, you can do any ray diagram that comes in your exams. It doesn't matter what type it is, you will be able to answer it yourself. It's as simple as that. So with that said, people, with this knowledge, let's go ahead and find out what are the different ray diagrams that you can possibly get for a concave mirror. First case first, let's say that the object is at infinity. Let's say there is an object which is very, very far away. It could be the sun. Let's say you have a concave mirror and this concave mirror is placed under the sunlight. Now the sun is very, very far away. Sun is about 150 million kilometers away. 150 million kilometers away, which is very, very far. Now, when an object is this far, we will only consider those rays of light which are parallel to the principal axis. Alright, now you tell me guys, if a ray of light is parallel to the principal axis, after reflection, what will happen to this ray of light? If it is parallel to the principal axis, what will happen to this? Quickly, what will happen? If it is parallel to the principal axis, exactly, it is going to pass through the focus. So, you see this? Two rays of light parallel to the principal axis. Where are they passing through? The focus. So where will the image be formed? Exactly at the focus. Now you tell me guys, here just by looking at the image, what can you tell me about this image? What can you tell me about this image? Just by looking at this, what are the things that you can tell me about this image? Yes, it's formed at the focus. Exactly, it's real. Because the rays of light are actually meeting. They are also inverted in nature. Exactly, Subhashri, absolutely fantastic. It is also diminished in nature. In fact, it is highly diminished. It's highly diminished. In other words, what you get is a point-sized image. Image so small that it's going to look like a point. This is the kind of image that you get when you have a concave mirror. And this is what is used. One of the applications of this is nothing but your solar cookers. In solar cookers, we are using the exact same thing. So you can see this. The cooker is placed exactly at the focus. We place it exactly at the focus so that all the rays of light after reflection is going to meet exactly at this focus and increase the temperature so that you can cook the food much more faster. Understanding? That is why they don't keep the cooker on the surface. They keep it exactly at the focus so that after reflection, because the rays of light are coming from the sun, so after reflection, they'll fall exactly at the focus and increase the temperature. Yes, this is a pretty big one. Generally, it's very small. This is a pretty big one. So this is this is the kind of solar cooker that Kali would use. Kali, the WWE hero, getting it? Because he needs so much of food, no? Like that. Understanding? Exactly. This is Kali wala. We'll call this KC, Kali cooker. Alright. Exactly. The great Kali. Exactly. It's not Kali, it's Kali. Kali, no? It's Kali. Sorry. Wrong pronunciation. Alright. Second one, guys. Let's say we bring the object a little closer now. Now, every single ray diagram, we're going to bring the object closer and closer. Now the object is at infinity. Now we'll bring it a little closer. This position, you can say that is just behind C or beyond C, beyond the center of curvature, or you can say that the object is placed between center of curvature and infinity. Simple. The object is placed between center of curvature and infinity. In this case, how will the ray diagram look? Now here, I'm going to use two ray diagrams. One which is parallel to the principal axis, another one passing through the center of curvature. The two standard incident rays, no? The first one and the third one. So I'll use the first one and the third one. So these are the two standard incident rays I'm going to use over here. So if you look at this, a ray of light parallel to principal axis after reflection passes through the focus. And that's exactly what happens over here also. A ray of light parallel to principal axis after reflection, it is passing through the focus. First one. Another one is a ray of light passing through the center of curvature. If a ray of light is passing through center of curvature, what will happen, people? After reflection, what's going to happen to that ray of light? Quickly in the chat box now. If a ray of light is passing through the center of curvature, what will happen to that ray of light? Quickly in the chat box, put it on, guys. Quickly in the chat box, put on. What is going to happen? What? Exactly. It'll retrace. It'll go back in the exact same path. And that's exactly what happens over here also. You see this? This ray of light is tracing back the exact same path. So where are these two rays of light meeting? Where are they meeting now? Where are these two reflected ray of light meeting? Where are they meeting? Where? Exactly, Gauri. Exactly. Now. So the image in this case is going to be formed between the center of curvature and the focus. Now look at the image and tell me, guys, what are the properties of this image? Very quickly tell me, what are the properties of this image that you can see? From just by looking at this ray diagram, what can you say? Exactly again, it is real, it is inverted, and it is also diminished in nature. It's small. Small in physics is nothing but diminished. Diminished means small itself. It's just a synonym for the word small. That's all. Got it? That's the type of image that you get over here. As simple as this. Let's talk about the third now. Let's say I bring the object a little bit more closer. Now the object is just behind C. What if I keep the object exactly at C now? Exactly on C. Again, two ray diagrams. One ray of light parallel to principal axis. What's going to happen to this one? Same. We are going to use this one everywhere. This first one that you see over here, no, a ray of light parallel to principal axis, we will use this in every ray diagram. Every single ray diagram, be it concave mirror, convex mirror, this standard incident ray remains common everywhere. So one ray of light parallel to principal axis, it'll what? It'll pass through the focus. Absolutely right. One more ray of light passing through where? Passing through the focus. Why not passing through the center of curvature? Because if I take a ray of light passing through the center of curvature, the ray will look like this. Now this ray of light, will it ever undergo reflection? Will this ray of light ever undergo reflection? No. Why? Because the light is somewhere over there. This light is going in its own path wherever it wants. How will it meet? It'll never meet. Exactly. So what we're going to do is we're going to use the second standard incident ray, that is a ray of light passing through the focus. So if you have a ray of light passing through the focus, what's going to happen to that? After reflection, this ray of light will become parallel to the principal axis. So what's going to happen? These two rays of light will meet at a point exactly at C. In other words, people, if you keep the object at the center of curvature, the image will also be formed at the center of curvature itself. No change. Getting it? Now remember guys, this is the only condition. This is the only condition where the image and the object is formed at the exact same position. And not only that, people, exactly, Chaitanya, the size of the image is also the same. You see this? This is the height of the object. The height of the image is almost the same. So you can say that the image is also of the same size. It is real again, and it is also inverted in nature. That's what's going to happen. All right. This is what happens when the object is kept exactly at center of curvature. Now look, we'll bring it closer now. Next position is between center of curvature and focus. You have two rays. Now again, you're bringing the object closer and closer. Every single time you're bringing the object closer and closer. Now there's one thing that you can notice, guys. As I bring the object from infinity to beyond C to the center of curvature, you can see that the image formed is also going further and further away. Can you notice that? Because when the object is kept at infinity, the image was formed at the focus. When I took it, brought it a little closer, the image was formed between C and F. When I kept the object at C, the image is formed exactly at C. So as I bring the object closer and closer to the mirror, the image is also going further and further away. And yes, the size is also increasing. Exactly. The size of the image, you can see, is also getting bigger and bigger as you bring the object closer and closer. So now, when I keep the object between center of curvature and the focus, where is the image going to be formed and what is the type of image I'm going to get? First one is a ray of light parallel to principal axis. As always, that always remains same. A ray of light parallel to principal axis after reflection passes through the focus. One more ray of light I'm going to take, but this time passing through the center of curvature. But here's the thing. The center of curvature is behind the mirror. So here's what you're going to do. You're going to take a ray of light that is passing through the center of curvature like this. So initially this ray of light will meet exactly, it'll fall on the mirror. It gets reflected back and retraces the exact same step. Understanding? This is one thing that you need to remember, guys. Please remember this. We're going to take the second ray of light, which is again passing through the center of curvature, but this time the center of curvature is behind the mirror. All right. It is behind the mirror. It is not in front of, behind the object. It is not in front of the object. So here, the condition is going to be a little different. It's going to be a little different. So you'll have to remember this one simple thing because again, in your ray diagrams, you're going to need this. So here, the ray of light will fall on the mirror, retraces such a way that it is passing through the center of curvature. And where are these two rays of light meeting? They are meeting at a point beyond C. Beyond C. After the center of curvature, this ray of light is meeting. Now tell me, people, what are the properties of this image that you see? All right. Let's go. Come on, guys. Come on. What are the type of image that you can see over here? What is the properties of the image that you can see over here? Quickly, guys, quickly. Quickly, people, quickly. In the chat box. What is going to happen to this? What are the type of image? What are the properties of image? Exactly. It's again real. It is inverted and it is also enlarged in nature. Exactly, guys. Because the image is much more bigger than the object. It is much more bigger than the object, and hence you can say that the image is real, inverted and enlarged. Simple. Alright, guys, moving on to the next one, guys. Let's say I bring the object a little bit more closer now. This time the object is placed at the focus. If that is the case, where is the image going to be formed? Again, two rays of light. One parallel to principal axis after reflection passing through the focus. Second one passing through the center of curvature. Just like what we did before. Exactly the same thing. But this time, if you look at the reflected rays, people, you can say that the reflected rays are parallel to each other, aren't they? They're parallel to each other. Yes or no, people? Now tell me, if the rays of light are parallel to each other, where will the image be formed? Yes, people. Exactly. Now, wonderful, guys, wonderful. A big round of applause for all those who got the right answer. Super awesome, people. Exactly. If the rays of light are parallel to each other, then the image will be formed at infinity. Why at infinity? Because people, when you have two rays of light parallel to each other, you cannot say that they are perfectly parallel to each other. They're not perfectly parallel to each other. See, if you keep on extending these two rays of light, they are bound to meet at one point or another. Getting it? They're bound to meet at one point. So let's say that the focal length of this mirror is 20 centimeter. All right. The center of curvature of this mirror is around 40 centimeter then. The image might be formed at 1000 centimeters, or it can be formed at 150 centimeter. Now you tell me, guys, can you show 1000 centimeters on a piece of paper? In your exam sheet, can you show 1000 centimeters? You can't. So we assume that the image is formed at infinity. Getting it? That is why we are saying that it's at infinity. Now again, when I say infinity, it does not mean it's going on forever and ever. It will meet, but at some point very far away that you can't really show on your paper, and hence we are saying that the image is at infinity. Now again, if you look at the image, real, it is a real image again, because they are meeting at some point in infinity. So they are real. Real images are always inverted in nature. So here also it's going to be inverted. And last but not the least, it is going to be highly magnified. Not just magnified, but highly magnified. Getting it, people? It is going to be a highly magnified. It's going to be much bigger than the object. Got it? So this is the properties of the image that is formed when the object is placed at the focus. Last ray diagram, people, that's pretty much it. That's all. When the object is placed between the pole and focus. Now this, my friends, is the most different case of them all. Now it's like this, guys. Now in your examination, when you're writing your paper with full concentration, there'll be this one guy who stands up on his desk and asks for additional sheet. You know that. Now there'll be this one guy in class, for no reason, he would have asked for extra sheet. Additional sheet? Yeah, this is one guy, always there. No, every class will have this one namuna, one guy, exactly. One guy would be standing over there. Ma'am, extra sheet. Ma'am, additional sheet. Huh? This guy is that guy. This ray diagram, no, is that person. This is that one person who stands up in the middle of the class. Now you might be wondering, sir, what is there to write so much, right? You will be thinking, like, what is there so much to write? This guy still stands up. For no good reason, he'll still stand up and ask for additional sheet just for the sake of it. That is this guy, all right? Now what is so special about this is that, guys, in this case, all right, look at this carefully. Object is placed between focus and the pole. One ray of light parallel to principal axis. After reflection, passing through the focus. Second one, the ray of light passing through the center of curvature. After reflection, passes to the center of curvature. If you notice this, these two rays of light are going away from one another. They will never meet. So what we'll do is, we will force them to meet. We'll force them to meet. How do we force them to meet? We will extend these two rays of light behind the mirror. And when you extend these two rays of light behind the mirror, you see that they will meet at a point behind the mirror. Now, what is so special about this is, guys, this is the only case, in the case of a concave mirror, where you will get a virtual image. Why virtual? Because the rays of light are not actually meeting. Now, if you look at the size of the image, the size is also much more larger than the object. So you can say that it is also enlarged in nature. And last but not the least, it is also erect. What do you mean by erect? The object is also like this, above the principal axis, positive. Image is also above the principal axis. Because all this while, if you see, image was formed below the principal axis. Yes or no, people? Every single case below the principal axis. Here also below the principal axis. Here also below the principal axis. But this one namuna above the principal axis. Exactly. The Shah Rukh Khan, right? Abhishek sir's explanation. Shah Rukh Khan. Exactly, guys. This is that one person which is different. Now, to give you an example of this one, guys, right now I have a concave mirror with me. If you notice very carefully, people, if you notice again, when I bring this object really close to this, you can see that, right? It is much more, the camera that I have, the webcam, is really not that big. But you can see this, it's highly enlarged. It is erect also, it's upright. It is upright. And it is also bigger. It is virtual. It is virtual in nature. That is why you're able to see the image on the mirror itself. This is the best example. But as I take it further and further away, once I go beyond it, you can see this. It is inverted now. It is inverted now. It is inverted. That is what happens. Getting it, people? So these are all the ray diagrams. Exactly. This is where, your dentist, your ENTs and all that, they use this type of mirror. Not only ENTs also, if you talk about shaving mirrors also, in shaving mirrors also, we keep the object that you have to stand really close in shaving mirrors as well. Shaving mirrors in the sense, the concave mirrors that you have, in that also we actually stand very close to the mirror, so you can actually see an enlarged image of your face, so you can see where you have missed out any spot or not. All right, so these are all the ray diagrams, people, all the details that you need in simple 30 minutes. I believe I took about 45 minutes. Oh, I took a lot of time. So please take a screenshot of those people. Please, not TNT, ENT it seems. Why would I blow off the room? ENT stands for ear, nose and tongue. ENT. Why would you need mirrors in TNT? Why? Why da? TNT. ENT. They have this mirror, no, they see inside your ears. That also they use the same thing. All right. Okay, so people, these are all the image properties, image positions and object positions. Please take a screenshot of this. Very, very important. This one page is enough for you guys to, refer while you're doing your, while you're preparing for your exams and stuff. Take a screenshot of this, keep it with you so you understand this. All right. Yeah, Sanjay, what is your doubt? All right. Anyways, so that's it, people. That was all the ray diagrams. I hope it makes sense. I mean, again, let me know, people. Was it easier this way? Again, please let me know if you did not understand anything. But I'm hoping that you've understood everything, people. If you have a doubt, please let me know right now. We'll try to sort it out before we get into the quiz. All good? So yes, people, all you need to do is this. Don't by heart it. Please remember the 3 standard incident rays. That is enough. If you remember the 3 standard incident rays, you can do any ray diagram. And majority of the time, you're going to be using the first and the third one. 90% of the time, you're going to be using the first and the third one. The only case where you're using the second one is the third ray diagram, where the object is kept at the center of curvature. Otherwise, every time, if you notice, you're using that one itself. You're using the first and the third one. So if you remember that very clearly, if you remember those 3 standard incident rays, you would actually understand and do everything, about ray diagrams. Absolutely easy. It's as simple as that. All right. Okay, guys. That said, let's go on to the quiz questions right now. So let me ask you this question. Are you guys ready for the quizzes? Ready? Can I get a yeah? All right, all those who are watching the session on YouTube, please join the live session on the platform so you can actually take part in the quizzes as well. Or else you'll just sit and watch. That's all. All right. Okay, guys. So here is the first quiz question for today. If the image is formed in front of the mirror, then the image distance will be positive, negative or negative depending on the size of the object, or neither positive or negative. Now think about the sign convention, people, and tell me if the image is formed in front of the mirror, the image distance that you take will be positive or negative depending on the size of the object, neither positive nor negative. Think about it, guys. I'll start the quiz in 3, 2, 1. Think about the sign convention about the Cartesian planes. 3, 2, 1. Let's go. Come on. Let's go, guys. Let's go. All right. Let's go, people. Okay, 20 more seconds. Almost 80% of the class has already answered, and apparently our very own Chintu Bhaiya is also online. He's also live right now. Chintu Bhaiya is also live. So we'll try to wrap it up very quickly so that Chintu Bhaiya can go ahead with this. All right, done, people. Super awesome. Bhumi, Kamal, Gauri, Subhashri, Devesh, Chaitanya, Navya, Onik. Cool name. Aditya and Michelle, congratulations. We have 68%. Not a bad start at all, people. You guys are just warming up, and yes, the answer is going to be negative, people. Why? Because like I told you before, according to the Cartesian planes, front negative, back positive. Exactly the same over here also. In front of the mirror, negative. Behind the mirror, positive. Above the mirror, positive. Below the mirror, negative. As simple as that. X dash, X, Y, Y dash. That's all. Second question. Here's another one. Focal length of a concave mirror is positive, negative, depends on the position of the object, depends on the position of the image. The focal length of a concave mirror. When you talk about a concave mirror, the focal length is going to be positive, negative, depends on the position of the object, depends on the position of the image. I have given you the hint also, people, so go ahead and do this. I'll start the quiz in 3, 2, 1. Let's go. Come on. The focal length of a concave mirror is taken as positive, negative, depends on the position of the object, or depends on the position of the image. 94% of the class has already answered. Whoever hasn't answered yet, please answer quickly, guys. I'll end the quiz in 5 more seconds because pretty much all of you guys have answered. 94 has already answered. In 3, 2, 1. Fantastic, people. Fantastic. Gauri, Chaitanya, Subhashri, Onik. Then we have Saumya, Aditya, Bhumi, Michelle, Kamal, and Chandra. Unfortunately, Chaitanya and Gauri chose the wrong answer. But the answer is B, guys. 75%. Fabulous, guys. Fabulous. Much better than the previous one. Exactly. It's going to be negative because focal length of a concave mirror lies in front of the mirror, and all distance in front of the mirror is negative. So focal length will also be negative. But why this confusion? Third one. What condition is necessary for a real image in the case of a concave mirror? The object smaller than its image, the object bigger than its image, object inside the focus, or object outside the focus. What is the necessary condition in order for you to get a real image which is placed in front of a concave mirror? Object smaller than the image, object bigger than the image, object inside the focus, or object outside the focus. Go ahead, people. Super easy question. Remember the SRK case? Remember that one guy who stands up, asks for extra sheet? That guy. I'll start the quiz in 3, 2, 1. Let's go, people. Let's go. Opposite of that guy. By the opposite of that guy. All right. Let's go. Come on, people. Come on. Quickly. In the chat box. Hi, Advait. What's up, dad? All right, 18 more seconds. 94% again has answered the question. I'll give you another 5 more seconds. You guys are super duper quick. In 3, 2, 1, time's up. Here we go, guys. Bhumi, Chaitanya, Subhashri, Onik, Michelle, Kamal, Arpan, Devesh, Aditya, and Gauri. Fabulous job. Overall, 52%. When I saw the fastest fingers list, I had a lot more hope. 52% is not bad, but could have been a lot better. It's okay. Not bad at all. Not bad. We can probably give you guys a thumbs up for it. Like, okay. Not that great. but it's still all right. More than 50% of the class. But yes, the answer to this question, guys, is outside the focus, because once you go between the focus and the pole, once you get into the focus, then the image that you get is going to be a virtual image, right? Like I told you before, it's going to be a virtual image. Because any object placed between the focus and pole will be virtual, enlarged, and erect in nature. Last question, people, last but definitely not the least. Here it is. When an object is held very close to a concave mirror, very close to the concave mirror, the image is smaller and inverted, smaller and upright, larger and upright, or small, same size and upright. The same question as before, but the same case as before. You just need to remember the image properties of the image, and you would be able to get this right. I'll start the quiz in 3, 2, 1. Let us go, people. Let us go. Smaller and inverted, smaller and upright, larger and upright, same size and upright. 93% in the first 5 to 7 seconds. Is this fabulous? What speed? All right. 0.25 seconds, 0.29 seconds, 0.3 seconds, not even 1 second time. You're getting, not even 1 second. Those are all milliseconds. Bhumi, Subhashi, Bashel, Aditya, Kamal, and Soumya got the right answer. Devesh, Onik, Navya, and Gari. Happens. It's okay. Don't feel bad. 66% though. I don't know what is this magic, what is this interrelationship, I don't know. It's inversely proportional to each other. If the fastest fingers list have more number of right answers, then the overall percentage will be less. If overall percentage is high, fastest fingers will be less. It's okay. Congratulations nonetheless. The answer is, guys, it's going to be larger and upright, because when the object is placed between the focus and pole, in that case, the image will be virtual. It is going to be erect, and it is also going to be enlarged in nature. All right, it's going to be enlarged. All right, so that is the answer, guys. With that said, here is your final leaderboard for today. We'll have a smaller drum roll for this. Let's go. The leaderboard is this. Bhumi with the first position with 360 points, followed by Subhashri with 340, followed by Michelle and Aditya with 280, followed by Kamal with 260, Onik with 220, Soumya with 200, Chandra with 180, Gauri and Alia with 140, Devesh with 120, Arun with 100, Chaitanya, Sarvagnya and Navya with 60 points. Fabulous job, guys. Fabulous job. Super duper amazing. Super proud of you guys. Keep it up. But we're not done yet, because I also have a homework question for you people. This is your homework question for today. What is the nature of incident trace when the object is at infinity? What is going to be the nature of the incident trace when the object is going to be at infinity? Put it down in the comment section, not in the chat box, in the comment section of today's session. So the next session that I come live, I'll be putting up these names in the start as homework rockers section when we get into it. So you guys can see yourself and make yourselves proud. All right, you're going to become famous. All right, so put it out in the chat box, in the comment section of today's video. What is the nature of incident trace when the object is at infinity is the question. Put it down in the comment section later. All right. With that said, people, now if you guys enjoyed the session so far, do not forget to hit the like button, subscribe to the channel as well. And if you want more such sessions in an amazing manner, you guys can take part or enroll yourself into the Pro Light CBSE courses, where if you go to the description of this video, you can see that for yourself. Pro Light CBSE class 10, class 2020 to 2023. The course at this point of time, people, offers a wide variety of sessions where you have physics, chemistry, bio, English, social science, all 6 subjects being covered in its entirety. Every single thing, every single NCERT topics would be covered in these sessions. Prepare yourself for a fun-packed, a super blastic sessions with some amazing set of master teachers, where you get not only the live sessions, you also get live doubt solving within the session, and you also get study materials with tests, all of it included in packed and packaged in a manner that you will be able to easily understand every single concept taught in the session. The course is set to start from 20th of June. So the next batch is starting from 20th of June. So you have enough amount of time to prepare yourself and to get started. Until then, you'll also be getting the recordings of it. This is for the entire year. The entire year, doubt solving, midterm revision, end-term revision, live quiz and leaderboard, tests and its solution with assignments. All of this for 4,500 rupees. You heard that right, people. For the entire year, not for a month, not for 2 months, not for 3 months, the entire course for just 4,500 rupees. And that too after 10% discount, you're getting it. Because the minute you click on that link, people, automatically my coupon code AME Pros applied, which means 500 rupees discount right there and then. So out of 5,000 rupees, 10% discount, 500 rupees already gone. What is left is 4,500 rupees, and that is what you're paying through any of the payment methods that you want to do. That's all you got to do to kickstart your 10th standard journey right away. All of it, master classes with all of this, micro courses, all of this would be available for you guys, and you can watch the session at any point of time. You miss a session, don't worry. You can get the notes, and you can also watch the replay of it whenever you want. At the comfort of your home, you're getting the best of best education. With that, you're also getting Vedantu's improvement promise, which states that if you attend the sessions and if you don't get the desired marks, you can even get this 4,500 rupees back. It'll be admitted, it'll be given back to your account through the original payment. However you paid, you'll be getting it back, because that is the kind of confidence that we have that if you attend the sessions, you will definitely see an improvement in your score and in your overall outlook to your education. All right. So that's it from my side. The course price might not stay as 4,500 forever, because it's definitely going to change. But that's pretty much it from our side, guys. Thanks a lot for joining. Catch you guys in the next one. Until we meet next time. Take care. Have a blast. And see you soon. All right. Peace. Bye, people. Take care. Enjoy yourself. Take care. Adios. Konnichiwa. Arigato.